Why does letting steak cool after cooking make it juicier? Let's uncover this delicious scientific mystery. Picture a perfectly seared steak, just off the grill, with steam rising and juices bubbling. The paradox is this: letting it cool actually makes it juicier. Let's start by understanding what seems contradictory about resting meat. Our intuition tells us that hot things hold more liquid, like how hot water dissolves more sugar than cold water. But the reality is that meat rested for 5 to 10 minutes loses dramatically less juice when you cut into it. When we cut steak immediately, juices pour out onto the plate. But when rested, those same juices stay inside the meat. So the key question is, why does cooling the meat improve its ability to retain juice? To answer this, we need to understand what meat actually is at a microscopic level. Meat consists of long muscle fiber bundles running parallel to each other, with water trapped between and within these fibers. These muscle fibers are made of protein strands called myofibrils that can contract and relax. Water molecules are held in place by hydrogen bonds with these protein structures, creating what we call bound water. Chemically, meat is approximately 75% water, 20% protein, and 5% fat. Now let's see what happens to this structure when we apply heat. When we cook meat, we're applying intense heat that causes dramatic changes to the protein structure. Starting at about 40 degrees Celsius, proteins begin to denature, meaning they unfold from their tightly packed structure. At 60 degrees Celsius, muscle fibers contract significantly, physically squeezing out water like wringing a towel. Above 70 degrees Celsius, we reach maximum contraction and the proteins coagulate into new rigid structures. The juice loss is roughly proportional to temperature squared, meaning small temperature increases cause dramatically more juice loss. The fibers contract dramatically, becoming shorter and tighter, forcing water out from between them. The key to understanding the paradox lies in pressure dynamics inside the meat. When cooking, high temperatures cause water and other fluids to expand rapidly, creating significant internal pressure. Following the ideal gas approximation, pressure equals density times the gas constant times temperature. At an internal temperature of 70 degrees Celsius, the pressure inside the meat is approximately 1.2 atmospheres. Imagine the inside of hot meat as a pressurized system, with forces pushing outward in all directions. Now here's the critical question. What happens when we cut into this highly pressurized meat immediately after cooking? Cutting hot meat immediately creates a catastrophic pressure release. When the knife cuts through, it creates an opening for the high-pressure fluids to escape rapidly. The immediate pressure drop causes rapid fluid expulsion, like opening a shaken soda bottle. The rate of pressure change equals negative K times the pressure difference, where K depends on the opening size. When cut immediately after cooking, meat can lose 25 to 40% of its total moisture content onto the cutting board. Now let's understand what happens during the resting period that changes everything. During resting, the meat sits undisturbed, usually covered loosely with foil, allowing crucial changes to occur. The temperature gradually decreases from about 70 degrees Celsius to about 55 degrees Celsius over 10 minutes. As the temperature drops, the pressure normalizes because the fluids cool and contract back to normal volume. Pressure as a function of time equals initial pressure times E to the negative T over tau, where tau is the cooling time constant. For a typical steak, tau is about 3 to 5 minutes, meaning pressure drops significantly in this time frame. But pressure normalization is only half the story. Protein relaxation is equally important. The contracted protein fibers partially relax as they cool, like a tense muscle relaxing after exercise. Myosin proteins, which contracted tightly during cooking, unfold slightly at lower temperatures, regaining some flexibility. This partial relaxation creates new microscopic spaces where water can be reabsorbed back into the protein matrix. The relaxation follows an exponential curve, where A is maximum relaxation and tau R is the relaxation time constant. During resting, capillary action redistributes juices throughout the meat. Water naturally flows from high-pressure regions in the meat's center toward lower-pressure areas near the surface. Velocity vector equals negative K over mu times the gradient of pressure, known as Darcy's law for flow through porous media. Think of it like a sponge that was squeezed. When pressure releases, the liquid redistributes evenly throughout. This redistribution process takes 5 to 10 minutes for a typical steak, which is why that's the recommended resting time. There's another important player in juice retention: myoglobin, the protein that gives meat its red color. Myoglobin is a protein that binds to water molecules through its charged amino acid side chains. When myoglobin gets hot, it denatures and releases the water molecules it normally holds. As it cools during resting, myoglobin partially renatures and can rebind some of that released water. Water binding capacity is proportional to the concentration of native, properly folded myoglobin. Here's something interesting. Resting also solves a temperature gradient problem. When you first remove meat from heat, the center is much hotter than the edges, creating a steep temperature gradient. Immediately after cooking, the center might be 70 degrees, while the surface is only 50 degrees Celsius. Temperature change over time equals alpha times the Laplacian of temperature, which is the heat diffusion equation. The thermal diffusivity of meat is approximately 1.4 times 10 to the negative 7 square meters per second. During resting, heat flows from the hot center to cooler edges, equalizing temperature throughout the meat. Let's put some real numbers to this phenomenon to see how dramatic the effect really is. Consider a controlled experiment with a 200-gram steak cooked to 70 degrees Celsius internal temperature. Cut immediately, the steak loses about 50 milliliters of juice. Rest it 10 minutes, and it loses only 15 milliliters. That means resting improves juice retention to 30% compared to immediate cutting, a dramatic difference. In other words, you lose 70% less juice just by waiting 10 minutes. That's a huge improvement for such a simple step. There's a bonus benefit to resting that relates to carryover cooking. After removing meat from heat, the internal temperature continues rising 3 to 5 degrees Celsius due to residual heat. This graph shows temperature continuing to rise after heat removal, then gradually declining during rest. This carryover effect allows the center to finish cooking gently without overcooking the outer layers. The carryover temperature increase is typically 3 to 5 degrees Celsius for medium-sized cuts. So how long should you actually rest different cuts of meat? Let's break it down. Thin cuts need about 5 minutes, standard steaks need 10 minutes, and large roasts need 20 to 30 minutes of resting. A rough formula: resting time in minutes equals approximately 0.05 times the mass in grams. For example, a 200-gram steak needs about 10 minutes of resting time. A 2-kilogram roast would theoretically need 100 minutes, but 30 minutes is the practical maximum to prevent excessive cooling. Let's summarize the physics that makes this paradox work. 4 key mechanisms work together: pressure drop, protein relaxation, juice redistribution, and temperature equalization. Final juiciness is a function of pressure, temperature, time, and protein density. All these factors improve simultaneously during the resting period, creating the paradoxical effect. Let's address some common misconceptions about resting meat. Myth number 1. Resting makes meat cold and unappetizing. Actually, a 10-minute rest only drops temperature by 10 to 15 degrees. The meat remains very warm, typically around 55 to 60 degrees Celsius, which is perfectly pleasant to eat. Myth number 2. Resting only matters for large roasts. In fact, even thin steaks benefit significantly. Even a 5-minute rest for thin cuts can reduce juice loss by 40 to 50%. For those interested in the deeper molecular mechanisms, let's go one level deeper. At the molecular level, water molecules, shown in blue, interact with protein strands through hydrogen bonds. Each hydrogen bond has about 20 kilojoules per mole of binding energy. The bond energy is 20 kilojoules per mole. At high temperatures, thermal energy exceeds bond energy, allowing water molecules to escape from protein binding sites. At lower temperatures, bond energy exceeds thermal energy, allowing water to rebind to available protein sites. Let's see how professional chefs apply this science in real kitchens. Professional chefs tent rested meat loosely with foil, which retains heat while allowing some steam to escape. Loose foil retains about 70% of the heat, while allowing steam to escape, preventing the meat from becoming soggy. Tight wrapping traps all steam, which makes the exterior soggy and defeats the purpose. No covering at all causes heat loss too quickly, dropping below 50 degrees Celsius and making the meat lukewarm. Let's calculate the actual energy involved in the juice loss process. Consider the energy required to expel 50 milliliters of water from a hot steak. Energy equals mass times specific heat times temperature change, plus mass times latent heat of vaporization. With mass 50 grams, specific heat 4.18 joules per gram Celsius, temperature change 30 degrees, and latent heat 2,260 joules per gram. Energy equals 50 times 4.18 times 30, plus 50 times 0.1 times 2,260, where 0.1 represents partial vaporization. This gives approximately 17,570 joules of energy lost with the escaping juice. That's enough energy to boil 100 milliliters of water from room temperature. So let's finally resolve this apparent paradox once and for all. The paradox is resolved by understanding the complex interplay of pressure dynamics, protein relaxation, and juice redistribution during the resting phase.